Hello everyone, welcome back to another Learning Glass episode. So, today we'll talk about batteries and something more general to batteries is electrochemistry. That's how batteries work, electrochemical processes. And you can describe the thermodynamics based on electrochemical reactions that can be applied in many different devices. So thermodynamics, equilibrium. Thermodynamics tells you where equilibrium lies, and for reactions, so for thermal equilibrium, that tells you when all the masses get the same temperature. For chemical equilibrium, it tells you at a given temperature and pressure what the concentrations are of each of the components of the reaction. The products, it could be a mixture of products and reactants that lie somewhere in between starting conditions and pure reactant completion. That's chemical equilibrium. And then for electrochemistry, you also have this charge balance, and you can use that to understand the voltage of an electrochemical system at equilibrium. So, and most of the time, our huge area of electrochemistry is interfaces between two different layers that react across a surface. So most batteries, they operate with a liquid electrolyte and a solid electrode, and that's the interface, the electrolyte on one side of liquid and a solid electrode on the other side, either as some porous material or some type of solid. So that's the interface, and that is a common characteristic of electrochemical devices. It could be a battery, could be a solar cell, could be fuel cells, and other types of situations where you have a interplay between the chemistry and electronic circuit. So one type of interface would be an electrode. Most of the time it's a porous electrode, but let's just say this is a flat plate. On this side it's the electrode as a flat plate, and then on this side you have liquid electrolyte. Doesn't have to be liquid, but many times it is. And in this electrolyte, what most electrolytes do is it's a liquid where you dissolve a salt in there. What a salt is that it dissolves into cations and anions, positive and negative ions, where overall the charge is neutral, balances those positive and negatives, but they are separate in the solution. So let's say you have an oxidized species. This will be O for oxidized. It has a certain charge, Z, and then you have the reduction, a product that it's a reduction process because you gain an electron. So let's say that has a charge of R, and in this process, it's an interface where you have the liquid components that are dissolved in the liquid electrolyte, and then the electrode gets involved because around the circuit comes an electron. So some certain number of electrons that you need to balance the charge there, then that goes into this Faradaic process. Then this O species loses an electron, and then this reduced species gains an electron. Where it loses charge, the gain comes from the outside, but so the gain of the electron goes to this R species. And if this is the thing that gets the electron, this would be gain of electron is reduction. So that means that the charge of O is greater than the charge of R because there's a negative charge that came into here. So it started off at O and it ended up at a different one. So it's starting from here. Then it got more negative because it started from here and it gained some amount of electrons. So this means that the final charge is smaller, more negative than it started off with. Okay, so that's this redox. Let's say that this is an oxidation reduction because this gets reduced and gets converted from this O species to the R species. So this would be a reduction at electrolyte interface. Then how you can write this chemical reaction is that you have, starting from this O species at this charge plus this number of electrons, creates this R species at a different charge. So that would be O, this thing, plus some number of electrons goes to this species that got reduced because it gained an electron at a new charge. So this is the number of electrons transferred. This is the starting species. We just call it O. And here is the product after reduction. So this is definitely reduced because it gained an electron. This doesn't necessarily lose an electron, but we just call it O because it's always a balance of the charge. There has to be a neutral overall balancing of what comes in and what comes out. We're not creating new charge in this reaction. It came from the outside circuit. Okay, so we can write it another way to say that a standard way to write this would be to put the electrons on one side. So it would be R with the the reduction. This is going to help us to put this all in standard formation. Like a general way to write these reactions, we'll put the electrons on one side and the products and reactants on the other side. Because the stoichiometric coefficient here would be negative because you're losing it and you're gaining this. You're destroying this, so the net production is negative, and you're creating this, so that's positive. Okay, so if we want to equilibrium, we're talking about equilibrium here. Equilibrium is quantified by chemical potential, where chemical potential of some species, by definition, it's the optimum of the Gibbs free energy. So when you change a small amount of this component, the moles, the number of the molecules of this, while keeping everything else constant, this is a way to keep track of the Gibbs free energy. And at equilibrium, this is equal to 0. So just reminding you where this Gibbs free energy where the chemical equilibrium is based on. It's based on the Gibbs free energy. What is the Gibbs free energy? It helps to quantify chemical equilibrium. And we have a video of that a few weeks ago. Then you can write use equilibrium at equilibrium you have the interfacial potential. So there's a certain voltage, because this is electrochemistry, it's not only a chemical potential, but this is electrons, Faradaic reactions, and we design these to have a voltage. So there's a certain voltage associated with this configuration at equilibrium. Okay, so what that is defined as, let's call this delta interface equals this potential of the we're talking about this here, there's an electrode and there's an electrolyte. Phi. That's the potential here in volts. Okay. Then, at equilibrium, the chemical potential is used to balance these things out. So also at equilibrium, you can say that the chemical potential of the reduced species minus the chemical potential of this oxidized, this O species, balances out the chemical potential of the electrons. So this is electron. So that's how you use chemical potential. Then, so how do we write the chemical potential? As discussed previously, from general balancing of the entropy and the enthalpy, and you can define this optimum here in terms of how the entropy has been defined as in terms of pressures and concentrations. You can use that derivation of the first and second law of thermodynamics, where entropy, you can express that in terms of temperatures, pressures, and concentrations. And then the enthalpy can be expressed in terms of specific heat. And when you do that, you can get an expression for the chemical potential, as we discussed last time. But I'm going to add on an additional potential just due to the voltage, the electronics part, the circuit part. That's what the difference between electrochemistry and just chemical reactions is you have this voltage potential literally in an electric circuit. So here, we're going to say the chemical potential of this R species is some standard potential. Let's call it this minus sign here. That's what Besant uses as a standard. Then the Boltzmann's constant times the temperature times the natural log of the concentration. It's not exactly the concentration, but it's basically the concentration. So then, so this is the chemistry's part. This is what we derived last time. But then, just because there's an electric circuit here, you also have some electrochemical potential or some electric potential based on literally just the voltage. So the amount of electrons you have, or it's proportional to the charge of one electron times the charges that you have, the number of charges that you have, times the unit charge of an electron, and whatever electric field voltage is set up. So this would be a standard chemical potential that you can find, you can relate to Gibbs free energy, or you can find from a table. Boltzmann's constant, temperatures. This is called activity, which is related to the concentration with the fudge factor to describe non-ideal behavior. And if we ignore the non-ideal behavior, and if it's dilute, you can say that it's ideal. You can basically call it the concentration. In a dilute solution, it's concentration. If you get more and more density of this particular species, the interactions between each of those R species affects the behavior, and that's what the activity keeps into account. But if it's dilute, it's the same thing as a concentration. Then this is the charge of that you have on that in the solution here, this charge. And this is the electrochemical potential. So it's literally the voltage in this due to that. So, so at equilibrium you have that. So this would be the standard, if there is no electrochemistry, this is how you would describe the chemical potential in a chemical reaction. And if you have an electric circuit, you have this electrical potential based on the charges that you have and the voltage potential that you have. Okay? So we can write this for M0 or MO as well. Where should I write that? So I'm going to say at here, at equilibrium, you have mu R minus mu O equals N times the chemical potential of the electron. So write that there and then erase all this stuff. So we have this starting species getting depleted, negative sign, gets converted to the end product is a reduced product because it gains an electron. And we wrote it in that way because that allows you to get a clear view of how this equilibrium works. It's a balance between the potentials of in this way. Then we can write the chemical potential of each one of those. MR is this. MO is similar, it's just corresponding, MO corresponding to the standard, plus this concentration effect, plus the charge of that species, and the chemical potential, electrochemical potential. Then for the electron, the chemical potential of the electron has some standard potential as well, some concentration effect, and we know the charge of an electron, it's 1, negative 1. Negative 1 times the unit charge and the potential due to electrons. So those are those three. So if we put that all together, so we use the definition of Gibbs free energy, the chemical potential depending on Gibbs free energy, and for chemical without a circuit, you don't have to worry about electrochemistry and voltage. But since we do have a circuit, we add on this voltage term, and then we're going to use that to find the potential voltage to having both the concentration effects, the standard chemical structure. So this would be just from like the chemical structure only. the identity of the molecule. It has a certain amount of, metal or like lithium cobalt oxide. It has a certain chemical potential just from that structure of the molecule. And it also has some contribution on the concentration. The higher the concentration, the more the chemical potential. And then the actual voltage in the system also affects that. And that is all going to be used to find this voltage. So let's write it here. Equals, now we're ready to plug all of those in. So another thing is that by charge conservation, we're not creating new charges, we're just balancing them out. You can write that ZR minus ZO equals the number of electrons that came in. So that's what's happening here. There's some reduction where there's some gain of electrons here, and this whole balance depends on how many came in, N electrons came in. So using all of that, we can write that this interface voltage at equilibrium equals the standard the electron standard minus the reduction standard and then what you get is a ratio between these because of you combine them this way, and then if you do the math with all of these natural logs, the natural log of MR minus the natural log of M0 or MO, you can convert that to a division, a ratio. And if we define this whole thing here as the not this standard, you would get, I'll write it here. At equilibrium, the interfacial electrochemical potential equals delta phi, this not thing, which is this term, you could do another math trick. You can bring this n outside of the natural log by multiplying it. That's a standard algebra conversion from natural log to the outside of the natural log. This will be n. So that's the equilibrium voltage. This is Nernst's equation. So in my family tree of professors, my professor's professor, whose professor's professors, they worked with Nernst, so that was cool. Nernst is a famous scientist. So what we did was, for this one process at an interface where you have this reduction product, you can define the equilibrium condition in terms of chemical potential, which is how you quantify chemical potential. Then we added this voltage potential contribution because we have a circuit, electrical circuit, and then it also depends on the other chemistry parts of what the molecule is and what the concentrations are. We applied that to the three things involved: the electrons coming in, the starting species O and the species that gets reduced, and putting that all together, you can define at equilibrium, there's this interface potential that depends on what these molecules are, what the identity is, the concentrations, and the potentials. So the electrochemical potential has this in here, and that's from the standard reduction tables. From one place you can get this is from high school standard reduction tables. That's where you get this from. So this is all what you can get from tables. It's the standard chemical potential plus an electrochemical potential that's standardized. And there should be data on that you can find and look up. Okay, so we're not done. So that's the interface of this one electrode. So we can apply the similar concept to an electrochemical cell. An electrochemical cell is a pair of electrodes. This is the half cell. The whole electrochemical cell is an anode and a cathode. So we can apply similar concepts to add up, okay, at equilibrium, what is the natural voltage just from the nature of the molecules we have and the nature of their standard reduction behavior, their known electrochemical potential. We did that for this side, then we'll combine it to both sides. And what that is it's called the open circuit voltage. What does open circuit means? It means that the current is not flowing. You do not allow you don't close the connection such that current can flow. You open the connection so that there's no current flowing, but as we know, there could be a voltage potential if there's no current flowing. And that is the open circuit voltage. Just by the virtue of having the certain identity of the molecule, that identity of the molecule has a chemical potential, and it also has, if it's in an electric circuit, an electrochemical potential. Okay, so open circuit voltage, let's call it VOC. What it is it's the natural equilibrium voltage. Natural equilibrium voltage. It's hard to read this natural. Rewrite it. So it's if we didn't have any current flowing, it'll be the potential just from combining these two electrodes together. Natural equilibrium voltage. And if you don't let the circuit flow, it'll just keep this natural voltage just because it has a certain molecule identity, energy level, and it has an electrochemical potential. So you would take the difference between the cathode interface with the electrolyte and the anode interface with the electrolyte. So that's what we call here, this interface. Let's just say C delta interface C delta interface A. Okay, so if we go back to this notation here, at the anode, the anode half cell, what happens is you have, at the anode, you have something that gets reduced. It gains an electron. So we write it this way, that some starting species at the anode loses an electron. So it goes from here to there. This is the product, or this way around. It loses, it becomes oxidized, or the end, this is the, it goes from, this is a gain of electron. It's this plus an electron becomes that, or the other way around. And then the cathode half cell would be that there's some O species at the cathode plus some electrons forms this reduced species at the cathode. So this is just saying that this subscript is saying is that it's at the different electrode. It's at the A electrode. This is at the C electrode, a different one. And by convention, you just write these going in this direction. At the anode, you're producing an electron. At the cathode, you're consuming an electron. That's why we have these electrons on either side. And then for the full cell, if you consider the system to be both electrodes, then the full cell reaction would be the electrons will cancel out. You would have Ra plus OC goes to OA plus RC. Okay, so we can use a similar concept that at equilibrium, you're going to have a ratio of products to reactants, and the open current potential would be depending on the cathode minus the anode. So if you apply the Nernst equation, it'll be the voltage just due to the electrochemical part. So it depends on just the identity of your electrodes and the concentrations. So that will be the Nernst equation applied to the whole cell. This is for the interface, half cell. This is whole cell. So what we did is this is all equilibrium. So assuming that everything self-organizes and you have a balance over time, all of the energies balance out and you reach equilibrium, this is what you would expect. You would expect the voltage depending on the identity of your electrodes and the concentrations of the ions in the solution. That's what these are here. And the temperature, of course. And this specific reaction that you define, whatever the identity is, you have to balance out the number of electrons going in and out. Okay, so that's the Nernst equation. Next time we'll talk more about the physics behind these batteries and the very simple, basic ways to understand them, because that's a starting point to learn how they are designed and how they work. Okay, see you next time.